Thank you so much for being here, Paul. Our next speaker is Dr. Paul Hessburg. Paul's a senior research landscape ecologist for the U.S. Forest Service Pacific Northwest Research Station. Paul's research explores wildfire and climate change effects on forest dynamics, resilient landscapes, and the ecology of forest reburning. In 2018, he was awarded the USDA Forest Service Chief's Distinguished Scientist Award. So we're pleased to have him here. Dr. Hessburg will discuss core principles for developing resilient landscapes. Morning, Paul.
Morning, thanks, Connie. My screen shared easily. Is that coming through?
Yes, it is.
Well, thank you very much for having me. And I'm excited to be able to share some ideas with SAF folks in Washington State. I'm gonna tell a story today about our inland Northwest forests. I'm gonna discuss some of their characteristics in the 1800s, 1900s, and today, and compare them. The reason of the story is that forests today are nothing like they were 100 or 150 years ago in the inland Northwest. And I'm going to show you some of those changes, what they mean, and what we can do about it. To begin, I want to show you some images. This is from Lookout Mountain area near Twist, Washington, and I'm showing a span of almost a century, 1930 to 2011. Here I want you to simply see that a grass-dominated landscape is now forested in the span of a century, a little more. Here I want you to see the strong effective topography. Dry south slopes and ridgetops have filled in with trees in low elevation pine and dry mixed conifer forests. Pretty stark. Varied forest age and density patchworks have been replaced with uniform mid-elevation moist mixed conifer forest. We don't see the varied successional patchwork. That's Mount Rainier in the background, both photos. This is the Slate Peak area, also Eastern Washington. People often say that the cold forests haven't changed much. These are cold forests in Eastern Washington, and here you can see patchworks of burned and recovering forest became continuous forest in upper elevation subalpine fir, lodgepole, Engelmann spruce forests. Even further up the hill, when we look at our subalpine forests, a lot of high meadows have given way to dense forests. Here's a close-up of some of those changes. We used to have areas of wet and dry meadows that were quite significant. In this scene, there are hundreds of times more trees than there were a century before. There have been many change agents that have influenced this between 1850 and the present day, but there are a few that really ring the bells. Timber harvesting of the large and the old fire-tolerant trees was a big deal. They were the target of most of that early harvesting. The loss of indigenous burning, starting with the spread of diseases in the 1700s and 1800s. In many areas, indigenous burning was a big deal. Domestic livestock grazing, cattle and sheep ate the grasses, which had been the historical conveyor belt for spreading fires. Development of the built environment occurred in many of these same places. And you layer onto that fire suppression. Together, these things operated to exclude fires along with a handful of other influences. And we layer onto that a warmer, drier, windier climate. And these conditions are steadily escalating in the 21st century. I'm going to show a basic idea of how the climate is influencing our wildfires. On the left, you can see low fire years. And this is when the potential evapotranspiration, that is what the vegetation is available to give up in evapotranspiration, is never exceeded by the actual. And the opposite occurs in the right panel. The high fire years are when the actual evapotranspiration exceeds what the potential of the veg cover is substantially. Fuels are available to burn early and longer, and we often have large, rapid spreading fires. In addition, we now know that when fire suppression was being spun up, we had great assistance from a cooler climate. Here you can see the early 20th to the early 21st century, and we're tracking area burned in hectares. It was a warm, dry climate, limited fire suppression before the 10 a.m. rule enacted about 1934 to 1935. And then you can see area burn goes through a steep decline for about 50 years, 1935 to 85. And area burned is not significant. And we think we have this wildfire problem pretty much licked. By about 1985, we see area burned going back up again. A lot of active fire suppression, burned area increases, and the climate is hotter and drier. What did that do to our inland Northwest forests? Connie, I think I caught you in this upper left photo right here. We know that the low severity fires occurred in low elevation dry forests. They were frequent, about every 5 to 25 years, and frequency reinforced low severity. If you had frequent fire, the fuels were regularly skipped off by fire, and the next impressive fire would likely be low as well. But we also saw that more extreme climate and fire weather events drove more extreme wildfires. So you can see that some moderate and high severity fires also occurred. And in the present day, the likelihood of low severity fires with the changes that I've shown you is much lower. And we see more moderate and high severity fire dominating that dry forest landscape. A little further up the hill in mid-elevation mixed conifer, we see moderate fire severity. Fires aren't as frequent because forests aren't available to burn quite as often. So we'll get fires every 20 to 50 years, and that tends to reinforce low and moderate severity because these are take some, leave some fires, not only in canopies, but also surface fuels. We also saw that we had more severe fires when we had more severe fire weather. So high severity fires were possible, as were low severity fires when the fire weather was more benign. And here we can see changes to the present day, very high likelihood of high severity fires under these conditions. I want to show you an important stabilizing feedback that occurred and has now been minimized. So locally in patches and in patch neighborhoods, more frequent fires continually thinned forest patches, and this reduced the density of trees, surface fuels, and fuel ladders. Bob Van Pelt has done a nice series of drawings to illustrate that, so I'll show them to you. So here's at time 0, we've got these open canopy conditions. We have low canopy bulk density, not a lot of surface fuels. Within the first couple of decades, we get an ignition. And we'll see the surface fuels, some of the snags, and fuel ladders will dry up, pretty much replicating the condition that we saw for. Then within the next couple of decades, we'll see another fire come along, again doing the same kind of thing, skipping off surface fuels, burning up some fuel ladders, but the medium and large size trees are genuinely surviving. And we end up having a similar condition persisting as a consequence of frequent low severity or moderate severity fires. And we keep fire out of the woods for a century or more, we end up with this condition. The trees that regenerated and released over that period of time now produce a more continuous cover, and fuel ladders are everywhere. So it's very likely that a surface fire will initiate and run a crown fire. Last, we have high severity fires. Wet and cold forests in the upper elevations experienced high severity fires. That was the norm. Fires were infrequent there, every 75 to 200, even more years. Because fuels were not as available to burn as often, mild climate and weather conditions would favor more variable fire severity and milder fires. And that gave us the variability we saw in cold forests. You can see that the likelihood of those less severe fires has changed. So there's another stabilizing feedback that's critical to talk about here. At a regional scale, fires created patchworks of non-forest, grassland, shrubland, young, middle-aged, and older forest, open and enclosed canopy conditions with hardwood patches. And these spatial patterns regulated the flow of fire on the landscape, the fire behavior attributes, fire size, and severity. So we have two feedbacks, a local and a broader scale feedback that have been minimized by this fire exclusion. And here's what happened. This is a look at forest cover types and how they've changed over a century. On the left here, you can see that ponderosa pine and grasslands are really quite abundant, and the landscape is full of fire-tolerant species. Ponderosa pine is in that green color. And then over time, we see these conditions change to conditions that look like this in the span of a century. Now the landscape is dominated by Douglas fir and grand fir cover as a consequence of those change agents. And these kinds of conditions abound. When we take a structural view of that landscape, we see that an all-age forest mosaic is replaced by a young multi-story forest, which is this color right here. And this is open canopy stem exclusion conditions here in this sort of grass color. And the changes that we observe over the span of a century in structure look like this. We see increased canopy cover, canopy layers, movement towards multi-layered shade-tolerant dominated patches, and we see that this multi-layered condition now dominates across the landscape. And here's an up-close look. This is on the Chelan Ranger District, and here I'm going to show you that there were only 3 trees here, here, and here in the historical scene. This landscape's never been harvested. And now you can see how this open stand has been replaced by Doug fir and grand fir that have filled in significantly that forest condition. Variable fire severity was replaced with high fire severity. In this scene, hot colors mean severe, cool colors, the opposite. And I simply want you to know that during the historical span, and you compare it to the current span, that fuel loading, crown fire potential, and flame length track the changes in the structure of the forest. So not only are individual watersheds more prone to severe fire because of high fuel loads and the potential for fires to get up in the crowns and run, but across the landscape, these conditions are well connected, they're contagious. And so watershed after watershed is affected in this way. These changes have influenced native insects and pathogens. I'll just breeze through a few. The western spruce budworm is a native to our forests, causes defoliation that looks like this. Large areas that are defoliated look like this. It's a native, its host range is throughout the western United States and on into British Columbia. And it was a native in our historical landscape. There was sort of moderate vulnerability to a number of areas, but the highly vulnerable patches were separated as a consequence of those patchworks that I showed you earlier. Now, conditions are more contagious, and we can see budworm outbreaks become wider, more chronic over time as a consequence of changes in the structure of the landscape and the species composition. Mountain pine beetle is another example of a native species in a non-native role. Large and severe and chronic outbreaks are a big deal now. We're familiar with the signs and symptoms of mountain pine beetle attack, but we're seeing landscapes that look like this over fairly large areas throughout large areas of lodgepole pine in the West. A native with a broad distribution. And we've seen that patches that were vulnerable to the mountain pine beetle have increased on the landscape as the forest matured in the absence of fire, and it's easier for beetles to be able to take out more patches on the landscape and create greater mortality than was typical historically. Dwarf mistletoes, also natives on the landscape. Here I'm showing Douglas fir dwarf mistletoe, mistletoe and ponderosa pine, and lodgepole pine. When you have more trees and more contiguous patches, and the trees are more densely packed and more layered, these are ideal scenarios for spread and intensification of dwarf mistletoes. Root diseases. I'll just mention three: Armillaria, Felinus, and Heterobasidion. A couple of these, the name tags have morphed, but I think most of the literature, and you know them most by these names, they commonly spread as natives in stands that have hosts in them, and they spread from tree to tree either by intertree root contact and mycelial spread or via rhizomorphs, these fungal roots that can go great distances through soil. They cause root rot, and you can see trees windthrow like this, or they cause standing dead mortality like you can see in some of these other photos. Once again, more shade tolerant trees packing the landscape in more layered stands, denser conditions, ideal for spread and intensification in Douglas fir and true firs. I also want to bring to your attention that non-forests are vital to resilient forest landscapes. Just for fun, I brought up a Osborne panorama from Mary's Peak, which is west of Corvallis in the Oregon Coast Range. Here we're looking north. And I want to show you, even on the west side, non-forest conditions, grasslands, shrublands, open conditions that don't meet the definition of a forest were really quite common. Same is true here in the interior on the east side. Why are non-forests important? Well, they occur on forest-capable sites after high-severity fires, and they look like this in the interior. Sometimes they look like this after a big bark beetle outbreak. So they occur as bare ground, wet and dry meadows, shrublands, savannas, or open woodlands, stand initiation or new forest structures, or you'll see them in mixes of these, and they can last from decades to centuries if they're maintained by fire. And the key idea here is if they're occurring in smaller patches, they persist for a short time. They're movable elements on the landscape. But if the patches are really large, they often persist for a very long time because they're influenced by lack of seed dispersal and reburning frequency. They're often touched by fire again and again, so forest regeneration doesn't obtain and forest conditions don't occur. Why are these conditions vital? We've done some research in most of the provinces of the inland Northwest, and what we found out through reconstructions is that non-forest was nearly as abundant as forest in some to most historical provinces. Some it even was more abundant than forest cover, for example, in some areas of the Klamath province. There's this interplay we're finding through our simulation modeling between ignition frequency, fire weather, and forest area with high canopy cover. If you will, there's a tug of war between factors growing forests and factors removing them with disturbance. And what I mean by that is that forests vary and provinces vary in how much potential energy they can store as forest. Non-forest becomes this benign fire delivery system when patches are within a patchwork of forest successional conditions, and their fuels are grassy and shrubby. They're ready to burn early in the season and often long. They're the first to cure out. They're the first to recover their moisture in the evening. They're really important for how they deliver fire and flame lengths to the forest that obtains across that landscape. And non-forest conditions are in flux with the climate and the fire weather. This interplay between non-forest and forest gives us clues to what we can expect with climate change. Warmer and drier conditions, we can expect even less forested area and lower canopy cover conditions than we see in the historical reconstructions. And regardless, the natural carrying capacity of forests is seldom realized historically, and that will be the case going forward as well. I want to be able to go through a handful of principles if you want to read up on them. We wrote a piece in 2015, it's here. But here I'm just going to briefly summarize them. What we've learned from our studies over the last several decades is that regional landscapes are multi-scale. Tree, clump, and gap patterns occur within patches, and these nest within forest successional patchworks. but these too nest within broad life form patchworks. And at these levels, fire influences the landscape. So when we talk about building resilient landscapes, we're really talking about rebuilding connections at each of these levels. We found that the topography provides a natural template for adapting vegetation and habitat conditions. And we can use the topography to tailor more characteristic successional conditions, density, life form patterns back to this landscape. We find that fire, forest successional patchworks, and climate, that interaction, that integral, that's the engine that drives the system. We create supportive life form and forest successional and fuel patterns, we adapt the fire regime. And then climate change will continue to adapt these, modify them, but in a more benign fashion than is currently the case. We find that predictable patch size distributions historically emerge from these landscape climate disturbance interactions. And restoring more typical distributions of successional patches allows us to adapt the current landscape to changing fire regimes and climatic regimes. The graph on the right shows what the patch size distributions looked like before the era of fire suppression. And with suppression, we're seeing that we're favoring more area burned in the larger patches. We've also learned that the patch size distributions of valley bottoms, ridge tops, north and south aspects is an excellent template for successional patch sizes. So we can literally use it to retailor patches to the landscape. Widely distributed large and old trees provide a critical backbone to the landscape. They're climate and wildfire adapted, and they're a strong genetic legacy. So making more of them is really critical. And to protect what remains, removing understory fuel ladders, duff and accumulated litter are important in dry and moist mixed conifer forests as well. Even though this is redundant of the first principle, I repeat it because it's really important. Successional patterns or successional patches are small landscapes within a larger landscape. In pine, interior dug fir, dry and moist mixed conifer patches, tree clump and gap variation is critical to influencing fire behavior within patches and within patch neighborhoods. So regenerating these, like you see on the right here, this is a slide from some of Derek Churchill's work. This allows us to be able to influence how fires spread and whether we have surface fires or active or passive ground fires within patches. Finally, land ownership and allocation patterns disrupt ecological boundaries. There's a need to work across ownerships and tenures to develop adaptation projects. This influences how we receive fire and how we send, as some of Alan Agar's great work has shown us. Some key takeaways. Adaptations are needed to create more characteristic life form patterns across the landscape, and we can use snow water equivalent and deficit predictions, which are now currently available throughout the West, to inform 21st century life form patterns. Let's look at this next example. These are slides from Derek Churchill, where he's showing us current snowpack and then predicted mid-century snowpack on top, left to right. And on the bottom, moisture deficit zones, current to mid-century. One of the things that you can see is that actually evapotranspiration in the red and some of the orange areas is going to exceed the potential of the vegetation. And this allows us to be able to transition some of these areas that are already dry forest away from forest conditions and into some of the non-forest conditions that I showed you earlier, rather than allowing fires to transition much larger areas to non-forest. That would be uncharacteristic. There's a need to create diverse patterns of forest successional conditions, open and closed canopies, that we can tailor to the topography. We have a need to rebuild hardwood forest patches where that's appropriate. They're very influential in the flow of fire on the landscape. We have the opportunity after fires and harvest to do that. Number 4, historical landscape complexity was the product of forest reburning. That means that fires overlapping other fires, fire-fire interactions, were very influential to producing the complex patchworks that we observed in the historical condition. Why is this important? Reburns decouple surface from canopy fuels over fairly substantial areas, and that allows forests to develop where there are very limited surface fuels as they initiate to be able to convey long flame lengths across the landscape and transition them to the crowns of the establishing forest. There are time-tested methods for creating these resilient landscapes. We know them well. Thinning and prescribed burning only as appropriate, and managing wildfires in backcountry locations, expanding areas of hardwood forests that are adapted to the conditions that are coming, and then working at sufficient pace and scale, applying the appropriate tools for the conditions that we encounter. And finally, last, we learned this from the indigenous burning and the cultural fire stewardship that went on in some areas for as much as 10,000 years. This is a transgenerational commitment to be able to create conditions that generations can maintain with maintenance treatments and the same kind of continued good work. All right, I think that's my last slide, and we've got time for some slides, do we? For some questions?
We do. So let me see. Does anyone have questions for Paul? All right.
Man, you're being too easy.
I know. Yeah, Paul's up for hard questions. Okay, I've got a raised hand here.
Thank you, Jeff.
Jeff, can you put your question in the chat, or are you just raising your hand? Okay, there you go.
I was having a problem turning my mic on and my video on. So Paul, thanks for that excellent presentation. It's always good to hear you speak, and yeah, it's to me it's kind of inspirational. I want to ask you about the changed landscape, right? And why we and why we manage the way we do today. So basically, I've always told people that when it comes to restoration, right, like coming from Region 3, they used to talk about a reference year or reference era, and we're trying to turn it back to that. To me, that's not as important as functional processes, right? I don't really care what the landscape looked like in 1898, except for the fact that natural processes were pretty much intact in certain areas. So my issue is the thing that comes to my mind is when I think about the owls and the intensity of our management and the focus on northern spotted owls, right? And if today's landscape is much changed from historic, just how we get that across, right? And maybe it's other values beyond like the northern spotted owl that today's forests offer that were not as prevalent 100 years ago, and just trying to get people to understand that mindset on how we manage. What are your thoughts on that? Because if certainly I'm told that northern spotted owl habitat today is far greater than it was 100 years ago, and I'm having to manage for today's conditions. Any thoughts on that? And maybe not just the spotted owl, but any other values that today's landscapes offer that were less prevalent, 100 years ago?
Sure. There's a handful of layered questions in there, and I'll try to peel them off one at a time. So probably one of the key ideas is that we look backwards and we study historical conditions so we can understand how forests interacted with fire. We can have clues to how various conditions responded to ignitions, fuel availability to burn, that sort of thing. It's very, very clear right now, so far in the 21st century, that the historical conditions of 1800 cannot persist well in the current climate. And there's a need to actually adapt the landscape looking forward. So an idea that I like to discuss is that we look backwards to understand how the woods work, how open canopy versus closed canopy conditions work, how species composition influence fire behavior, and use those things, but in a forward-looking way to actually create conditions that are adapted not to the historical climate, but to the one we're moving into. And that climate is going to have less forest and more open forest conditions on it. We're going to see dry pine sites move, in some cases, off the landscape, and we're going to see, in the current condition, become non-forest. We're going to see dry mixed conifer forests become even drier and more open. We're going to see moist mixed conifer become dry mixed conifer. And some cold forests are going to leave the mountain or be restricted in size, the mountaintop. That's what our downscaled climatologies are teaching us. In that light, another one of your questions is a lot of complex forest or fuel model 10 common in the historical climate or in the future climate? What we have today is more than we had 150 years ago or 200 years ago. And what we did have occurred in places that we call fire refugia, where the topography and the context surrounding those areas allowed patches to escape fire for longer periods of time than the surrounding landscape. We've done some research, and so have other colleagues of ours. But an awful lot of those refugial conditions and the appropriate context don't exist anymore because we've allowed forests to become denser and more contagious for the spread of fire. So the amount of late successional habitat that we had historically, we will not be able to store on the 21st century forests. And by the mid 21st century, if we do not adapt to more open canopy conditions on these dry ridge tops, on these dry south aspects, more late successional and complex forest habitat will be threatened by fire. And the problem is contagion. Dense, compact, overly treed conditions next to the same, and that allows for running crown fires to obtain. And so adapting the landscape to the fire regimes as they're shifting and the climate as it's shifting is job one in the 21st century. That about covered for you there, sir?
Yes, sir. I appreciate that. Thank you.
Yep.
Paul, we have a few more questions come in.
Righto.
Okay, so here's the first one. At a landscape level, how does the patchwork of land ownership impact the ability to restore the pattern of fire-driven structures? Does the variability in land ownership create a similar variability, or is the structure and spacing vastly different? And how is this changing the function and behavior of the forest?
That's a great question. That's why we spun up our last principle. Well, of course it changes it, right? We're on different plans. We have different goals. And so ownership and tenure influence the landscape by allowing less than ecological patterns to persist. And some kinds of vulnerabilities are associated with some kinds of patterns, regardless of our plan. And it's one of the reasons why we feel it's really important for interdigitated landowners to work really closely with each other, because wildfire and insect outbreaks are transmitted risks. We can transmit them from ownership to ownership. If we work together, what we can do is evaluate those conditions and still meet the majority of objectives, but reduce the vulnerability of certain land tenures and ownerships as a consequence of having simulated wildfires through those conditions and find out what conditions actually meet plan objectives across the ownerships. And so it's, if we don't do that, and with as much ownership that's not public in Washington and other Western states, we literally can't meet our objectives as well as we might hope without this this interconnected planning and implementation of treatments that allow us to have forests that persist.
All right, thank you, Paul. Another reason for shared stewardship.
Absolutely.
Okay, the next question. Are you concerned about decreased carbon sequestration opportunities with increasing non-forest lands?
That's a really great question. So the yardstick for carbon sequestration is not the modern landscape. It's actually a landscape of the West or Western North America with an active fire regime. That gives us greater insight to the kind of carbon that can be stored. Remember, I told you there's this push-pull, this tug-of-war between conditions, growing forest on capable sites, and disturbances taking them away. As the climate warms, more and more forest conditions are available to burn, and they will burn without adaptation to the conditions looking forward. So planting more trees and having more forest actually incites more severe fire spread if it's not done properly. And we're pretty sure, based on our reburn simulations, that the non-forests of the historical era, more area in non-forest will obtain as a consequence of a warming climate. That's what it's showing. In fact, without rebuilding that non-forest area, the landscape tips. It's robust if it's well configured, but it's fragile if it has too much forest loaded into it, and you lose far more forest as a consequence of overloading forest. So the stabilized carbon sequestration scenario is a climate adapted landscape, not an historical landscape and not a modern landscape. There's actually more opportunity to sequester carbon in that restabilized landscape.
Thank you. Quite a lot of nuance there.
Yep.
All right, so here's a management question. If prescribed burning is not available to us, would thinning, pruning, understory brush treatment, and slash treatment get us close?
It'd get us close, but no cigar. We have to figure out a couple ways to get fuel off the landscape. We have a big grant in Canada right now to look at how to store carbon better in stabilized forest, and a bioeconomy and storing it in structural materials is part of that calculus. One of the key things with thinning and pruning and doing all sorts of brush treatment and not really dealing with the accumulation of those surface fuels is that we still are going to have an awful lot of essentially wood put now newly on the ground to burn and release energy and long flames. And so we have to figure out ways either through burning or removal to be able to reduce those surface fuels. If you stop and think about it, the fires that we're concerned about are driven by flame length. And we know what kinds of flame length allow us to be able to directly interact with fire and those flame lengths that don't. And so the map of probable flame lengths is the landscape we want to manage for.
Okay, thank you. So a couple more. Any thoughts about whether future fires might change in timing, earlier or later, and how that might change sustainable forest structures in which existing plants and tree genetics have been molded by past fire timing?
That's a really great question, and there's so many aspects of that, whoever the questioner is, that we really don't know about. Because if you stop and think about it, if the climate isn't changing environmental conditions, then the map of potential vegetation types shifts on the landscape in the 21st century. And whether or not there are opportunities for migrations over the spaces where the shifts are occurring, it's a big black box. We don't know whether or not that's going to be possible. The landscape of 1700 was cultivated by millennia of fire that allowed those communities to develop and persist and have all the right apps to continue to persist. Sudden change really changes that scenario. We believe that helping the landscape to adapt rather than to allow fires to willy-nilly change the landscape is probably a better method than assuming that fires will just naturally fix the landscape. We just completed a grant evaluating post-fire landscapes. And what we're finding out is wildfire is a really blunt tool. Spatially, it's blunt. It doesn't apply the treatments that we really would like to have. And so we're getting conditions that we're thinking about managing forward that are really going to be quite difficult. They're going to require a fair amount of rehabilitation. So what we think is going to be true about future fires is that if we move in the direction of more sustainable composition, more sustainable structure, that we're going to have an advantage to better adapt more quickly to the coming wildfires. I think that's the best we know right now.
Okay, thank you, Paul. Questions are still coming in. So here's one. If you were a forester educating landowners to achieve their ownership needs, what fundamental advice would you convey to your clients that want to protect and enhance diverse wildlife values on small ownerships, 5 to 500 acres?
That's a great question. That was you, Andy, right? I am a forester and I have educated landowners. And what I basically tell them to do is you want to favor conditions that allow wildlife species you're interested in persisting. A lot of times that means the larger trees, the more fire tolerant species. When you have opportunities to leave snags, leave big ones. When you have opportunities to have down logs in the landscape, leave big ones. The smaller ones aren't as appropriate to many of the habitat needs, and they're also really fuely and they compromise the rest of the forest structure, whether it's dead or down. I'm assuming, Andy, that you're thinking perhaps of people who are interested in wildlife values of more late successional or older conditions. Is that accurate, or did I misinterpret you?
No, it's not necessarily late successional. It's just for being able to contribute to wildlife habitat in general. People like to watch wildlife, whether it's big game or songbirds, or know that they have a snag that has a little pygmy owl living in there. So you answered it when you identified some of the features. That's helpful. But sometimes the scale is something that's difficult to convey in terms of the real benefit of creating like an opening on a 20-acre parcel.
So here's another idea. Remember I showed you one of the principles that this clumpy, gappy forest cover is critical at a patch to patch neighborhood scale. Let's say, we're in the tens to hundreds of acres. We have the opportunity to essentially create a variety of different conditions, a salad bowl of ingredients, if you think about it, with that clumpy, gappy structure where clump sizes vary and gap sizes vary, where we're going to get patches with grasses and shrubs, mast species that are critical to some species of interest, right next to clumps of forest conditions. And I think that would be another thing that we could signal to them and say, if these are preferred values, also strive for that clumpy, gappy tree cover in the larger size classes.
Okay. Thanks to both of you. So the next question, next question is about soil. I suspect there is also a benefit of fire to the soil structure and composition. What do we know about soil health and the fire regime?
Another great question. These people thought about these questions before they asked them. That's wonderful. So we know that soil health is incredibly important. Severe fires are tough on it. Mild to moderate fires, much less so. And we also know that the carbon fraction of soils is enhanced where we have large areas that have a characteristic low to moderate severity fire regime. Because as these partially burned wood pieces erode over time, that we're adding carbon, and some of Tom DeLuca and others' work shows us that the carbon from the fire regime can last hundreds to more than 1,000, 1,500 years in soil. So that carbon is influential in storing moisture on sites that are otherwise relatively dry. So it's a pretty key deal. The severe fires have just an opposite influence. Beside the hydrophobicity that they bring after a severe fire of long duration, it's really difficult to build up on those dry sites the organic residues that took centuries and millennia to accumulate that are fairly important. Those frequent fires skiffed off the duff and litter. They didn't consume everything. So, and if you think about the duff and litter, it's important to contributing, at least at some level, to the development of the organic residues that develop in those soils that are so critical for tree growth.
Thank you, Paul. So the next question, I took a restoration silviculture class from Andrew Larson at the University of Montana years ago when he was working on his gap patch work. He mentioned that various Pacific Northwest national forests were interested in trying to recreate that spatial heterogeneity by mapping and modeling historic structure and implementing treatments accordingly. Have you seen any national forests trying to actively implement this?
I have, and you having Dr. Larson for a restoration silviculture class makes you a very lucky person. He and Derek and some other colleagues from Pacific Southwest and the American Southwest have been continuing work on these clumpy, gappy structures. Miles Lefebvre did some work reconstructing those patterns in moist mix conifer and found them there as well. They're really important, and increasingly, and Derek may even talk about this, they're developing all sorts of utilities to be able, so people can mark and implement these sorts of treatments, the ICO treatments, expeditiously. Yeah, they're growing in the frequency of application, and some of them have even been tested by fire and not been found wanting. So yes, they're increasing on a variety of forests in the inland Northwest, and in the Blue Mountains, we're seeing more implementation and so forth. So it's catching on, and it's smart stuff.
Great. Thank you, Paul. I think this is our last question. To flip the script, how does historical structure of riparian corridors in frequent fire areas look historically and look in future climate scenarios? Do these areas that cannot or are minimally managed become corridors of wildfire spread? Should we change our riparian management strategies or policies in dry Eastern Washington areas under climate projections?
That's from Sean, I'll bet. Another great question. So a great way, there's more research developing in understanding historical and modern era riparian settings. And the gist of it is that where you have vegetation that's influenced by hyporheic flow above 5% gradient, you have a true riparian setting. Above that, we're finding out increasingly that the fire regime of the adjacent upslope was the fire regime of that draw. So think of it in 1 to 5% gradients, riparian conditions have hyporheic flow, hyporheic influenced riparian vegetation communities. Above that, we start to see less of an influence of that riparian condition on the fire regime. And if you think about those areas that are influenced by hyporheic flow, we also see that fire is not the dominant disturbance agent. It's actually river processes, ice and debris flows and things like that that really influence. And many of these areas are actually influenced by hardwood trees and shrubs, not conifers. And so we see very, very different ecologies of place, different kinds of disturbance regimes. As the climate gets hotter and drier, we're going to see and floodplains get down cut, even in these low gradient reaches, we're seeing many of these areas getting dewatered. If we want those riparian conditions to persist, floodplain restoration is going to be a real key in these lower gradient reaches in order to be able to get the riparian species and the riverine processes to influence the disturbance ecology again. And sadly, many of these riparian areas are deeply downcut and dewatered as a consequence now. So you see vast conifer encroachment on them. So those are kind of important steps to be thinking about at the same time. And as we see riparian conditions changing, we're going to want to be able to modify how we influence those riparian conditions. So where the upslope process is likely the key to that draw, allowing those stand conditions to be climate tolerant and fire tolerant is actually going to be a key. That's not in the area of the low gradient reaches. It's above that area.
Okay, well, thank you very much, Paul. Thanks so much for being with us.
Yeah, thanks for having me. It's been fun.
It's been a pleasure to have you.